Good afternoon. Thanks a lot, Ms. Parvati Priya, for the opening remarks and introducing me. On behalf of the Department of Robotics and Automation Engineering, PSG College of Technology, I welcome you all to this 5-day FDP. Hopefully, all of you would have known about robotics, because robotics is not a new word. It has been there for almost 60 years in the industry. Anyway, when we are starting a robotic welding program, it will be apt to start with what is industrial robotics. So before that, I will start sharing you with what is our department, how old is this department, what we have done so far, major projects we have carried out, and then I'll proceed to the content. Then finally we have established a Center for Excellence in Welding Engineering and Technology, where we developed robotic solutions, automated welding machines. We have developed the welding power source and welding consumables. So we'll touch upon that also at the end. First of all, let me thank Dr. Murugan, who is authority on welding, and the last few years he has been a leader in robotic welding, or using robots in welding to achieve greater accuracy, precision, and making complex profiles possible. Also to other organizers of this program. So in case you have any questions in between, you can put it in the chat window, or you can interrupt me and ask me. So let us see what best we can do. Okay, so I'll making a presentation. My presentation is able to see that? Are you able to see that?
Yes, sir. Visible, sir. Yes, sir. Visible.
Okay.
Please put in full screen mode, sir.
Yeah. Just.
Yeah.
So the vision of the department is to be a leader in robotics and automation engineering education, and contribute to research and applications. Being this program, robotics and automation, it's quite a new program in India in the undergraduate curriculum, and it is basically an application-oriented course. The students of this 4-year BE program, they study theory of fundamentals of electrical, mechanical, computer science, and other elements. And several courses are oriented towards application of these technologies to the industry. So in that aspect, research projects finds a lot of applications here. So we have a quite number of funded research projects in the department. So that is, we still would like to be one of the world's leading institutions offering undergraduate programs in robotics and automation. We don't have any master's program right now. So to achieve the vision, our mission includes create opportunities for the students by imparting knowledge, experience, and skills to become the leaders in robotics education and research. So we understand that our brand ambassadors are our students. So if our students, they have the experience and skills necessary to become or take this technology in the industry, I think that will be one step towards achieving our vision. And to contribute to the global economy through meaningful partnerships with governments, institutions, and industry in robotics and automation fields. Okay. At a glance, if you see the program, inception was in 2011. So it is 9 years since the department was created. We have till last year, not including the current year, but till last year we have 341 graduates. This year another 60 will add to that to make it 400 graduates. And the numbers also will change here. The campus placement also has changed. So about 89 plus another 10, so around 100 students of this program have gone for higher studies. Most of them have done their masters in top universities in US, Germany, Australia. Interestingly, we have around 25 entrepreneurs who have come out from this new program. Our students as well as our faculty members have got various awards, prizes in various competitions or some skills test. We do have official internship MOUs with 8 universities. So that means that every year, the final year students, especially in their 8th semester, these students goes to 8 of these foreign universities. In US, we have Carnegie Mellon, Purdue, WPI, NYU, Michigan State University, and in Germany we have a group of 8 other institutes. We call it as a consortium of IGCHE, Indo-German Center for Higher Education. So several students, approximately about 15 to 20 students, they go abroad for their internship in foreign universities. The department has about 21 MOUs with industries. We have 11 centers with industry partners. We have currently about 263 students. The new first years will be joining soon. So that will make around 320 students. So that is a glance about the program and some of the snapshots of the major events. So twice our department has scored the best outgoing student of the institution. Then our students participated in the World Skills Olympiad in Brazil once, where we represented India in robotics event. Then several centers of excellence, several products. So this product is a Endo trainer, that is a surgical trainer robot the department developed in association with L&T Technologies. And this is a special purpose machine for welding, welding of circular objects like motor frames, any circular thing. We have 2 torches, so that maybe we designed it basically for the electric motors or pump manufacturers of Coimbatore. You know that Coimbatore has about 40% of India's pump manufacturers. So to support them, welding is one crucial process in that, circumferential welding. And availability of skilled welders are becoming less and less every day. And automation is the only solution. And this was a project or a product developed with government funding through the Department of Heavy Industries. And this robo is also a welding robo, which we have developed here. There are also other types of robots. We do offer a training program for school children in robotics. You can see one photograph of our first batch student working for Valkyrie mission for Mars by the NASA. So he's also in the he was there as a member of the team into development of robots. And there is another autonomous car which we were trying to develop for Mahindra as a part of the Mahindra Rise competition. These are some of the snapshots of what we have done so far. The faculty, unlike other conventional programs, we do have a pool of faculty members from different disciplines. We have faculty members with electrical background, electronics, computer science, mechatronics, and mechanical engineering. And their expertise is, you can see, under this following headings. 17 faculty members are there put together. 8 are having PhD, 2 are in the process. Sorry, 8 plus 2, 10 are having PhDs, 5 pursuing PhDs, and 25 full-time as well as part-time PhD scholars in the department. So out of the 17, 6 of the faculty members are with industry experience. If you see the average years of experience of the faculty members, it is around 14. We have 18 plus 1, 18, 19 sponsored projects to the tune of around 40 crore. We have around 20 project engineers altogether in working under various projects. So far, about 248 publications from all these faculty members. The faculty members actively participate in conferences, workshops, and other training programs. So the expertise of the faculty members, we have good strength in design, manufacturing, and industrial engineering. We do have a group working on sensors, machine vision, and image processing, because any robotic system, vision systems plays a major role. Then controllers and soft computing, there is another team. Then electrical machines, drives, and control systems, there is a good team. Welding is one area. If you take the application side of the robotics, we have identified 3 major areas. One is welding automation, welding robots. Basically, we call it as under the industrial robotics group. Another is mobile robots. Another team is on medical robots. So if you see the application expertise into industrial robots, mobile robots, and medical robots. They are my strength, the department's core group, and their expertise are shown here. These things, I think you can have a look in the website and you can get it. Just a sample of how the curriculum consists of, because most of you may be from other background, other core programs. So this is how the constitution of the curriculum. Basic sciences forms. Anyway, these are maybe as a standard ASCT's grouping. But if you see the courses, under mechanical stream, we have strength of materials, kinematics and dynamics, hydraulics and pneumatics, manufacturing technology, design of mechanical transmission systems. In the electrical stream, we have electrical machines and power systems, linear integrated circuits, automatic control systems, microprocessors and microcontrollers, power electronics and drives. Computer science stream, we have data structures and algorithms, embedded and real-time systems, Internet of Things, machine learning, AI. And under the automation, we have sensors and transducers, CNC machines, PLCs, automation system design, and TIA. Coming to the robotics group, we have robokinematics and dynamics, field and service robotics, industrial robotics and material handling systems, vision systems, and medical robotics. So these are major courses the students of this program goes through. At the end, once he or she completes this program, they are able to take up design, development of automation systems, as well as robots for various applications. Apart from the 3 credit courses, we do also have a system called the 1 credit course. So these courses are offered not from the department, but by experts of the discipline from various industries. So industrial experts, they come and deliver courses on these titles. And evaluation also will be done at the end. So these are, and one major thing what we practice in the department is that every course, a student when he goes through the program, he should do projects or mini projects. So that should satisfy, that will be a part of the assessment. So to make that possible, we have internships. We do have an innovation lab. Then in the 7th semester, there is a project work phase 1, and there is a project work, the major project in the 8th semester. This 8th semester project can be done. We prefer the students to go to industries, take up an industrial problem, and work on it. Also, the internships possibilities in foreign universities also can be explored. To make learning more practical, we do have several hardware facilities in the department. So these are some of the centers of excellence which we have set up in association with various leading industries in the field of automation and robotics. The first one is the PSG Siemens Center for Excellence in Automation. So this center houses PLCs, DCS, SCADA, and HMI systems. We do have application units where servo motors, stepper motors, induction motors with VFD or variable speed drives. Then PSG Adapt Center for Robotics has 2 robots with Omron and Adapt. One is a SCARA, another is a parallel kinematic robo. Then we have a center with Festo. This is called as PSG Festo Center for Robotronics, where we do have simulation stations, hardware stations where automation process can be simulated. We do have a Robotino industrial as well as mobile robots of Festo. Then another center is with PSG and Danfoss. So Danfoss is into energy saving as well as variable speed drives. So compressors, various types of industrial drives, these are available in the center. And Danfoss also conducts innovation competitions every year. So our students participate in that. And there is another center on welding, which I'll tell you more detail at the end of this program. And there is another center with ePlan. This is basically for automation software development. And another center with FANUC on CNC machines and robotics. And there is a E-Entra Center for Basic Robotics, where in the first year, the students of this program, they build, operate, test various types of mobile robots. Then there is a Hayden CNC Center, where they have a machine-like keyboards by which they can program and simulate CNC programs. And there is another center, the new one is on Beckhoff for industrial automation, where we can demonstrate Industry 4.0 also. These are the snapshots of the facilities available in the Center for Excellence in Welding Engineering and Technology. These are some of the achievements of the students, which I showed you in the first slide also, it was there. So now we'll start, that is about the department. So if you have any queries about the department, you can write to me or you can write a mail. Now we will start with the industrial robots. So in this presentation, I will be touching upon the introduction to robotics. Then with some history about how all this started. Then what are the various configurations of industrial robots available in the market, how to identify them, what are the applications of each, how to select robots for such applications, various applications. And what is a new technology in robotics? So this is what I intend to present to you in this presentation. Plus at the end, an introduction to the Center of Excellence in Welding Engineering and Technology. So when we hear the word robot, the first picture that comes to your mind will be something like this. A manipulator. It's a very popular industrial configuration.
System which develops but cannot have the ability to think and understand decisions.
Sorry. Is it a question?
So I mean to say that
Pardon?
it does not have feeling, sensation, senses.
I didn't get you, sorry. Can you repeat the question?
Sir, I want to know that does robots have the sensation and feelings?
Yeah, I'll come to that. Wait.
Okay, sir.
So far, no, when we are especially engineering college teachers, when what for us a robot means maybe like this, but before you start learning about industrial robots, since I think 1917s or from early 1900 onwards, there were several movies that presented us with a concept called robot. So some of the popular movies or science fiction movies where robots were employed or displayed, you can see here. The Indian, maybe the Yantran was the one which was a big hit with superstar Rajinikanth himself as a robo. So Robocop, Interstellar, these were all, most of these movies were super hits. And also there was a movie by, there was a movie, Modern Times, 1936, very comedy movie. So various directors, various concepts they presented, science fiction, action movies, comedy movies. And the word robot, that is still more older. It's not that robots are very new. So Karl Kapek in the year, that period where he lived up to 1938. So in the 1920s, he has published books as well as dramas. So in his dramas, he introduced the character, the robot. And later, most of the inventions of humans, you see, somebody would have dreamed about it. Once upon a time, it was a fantasy. Then it became a reality later. So unless you don't dream about something, so early days James Bond movies, if you see those days, it would have looked like fiction, but now it will be a reality. So man has this unique capability of fancying or fantasizing, and then we work towards that and make it a reality. Most of the things originated from nature. We observe nature very closely and try to replicate or reproduce things that are closer, that are available in the nature. So most of these movies, the robots were more intelligent. There are a lot of sensors, they have emotions. And what happens due to emotions? Hello? So it became a field of study later, and that was called as robotics. There is another science fiction novelist, Mr. Isaac Asimov, who popularized the word. From Karl Kapek to Isaac Kapek's were limited to dramas or plays. He used to write, used in the play, he used to write about it. But to the masses, it was taken by Isaac Asimov. So he started writing a lot of science fiction novels, which became a big hit those days. Even today, Isaac Asimov's novels are of very interesting. So he is the one who coined the fundamental laws of robots. If you remember, if you have seen the movie I, Robots, Will Smith tells you the 3 laws of robots. So fundamentally, these laws says that a robot should not harm a human being, even for its own existence, or if it is to protect somebody else. Basically, robots are like slaves. It should take the commands from people and protect the humans, or fundamentally they should not harm humans. But there are some movies like Robocop, or there are movies now, or even recent days we have drones which can attack humans. So yes, these laws are sometimes broken, but fundamentally when Isaac Asimov started writing these laws for his books, his major concern was never allow a robot to harm humans. If that happens, and as the speed at which the AI is moving, AI is expanding, or AI is becoming more and more powerful, maybe like iRobots, a stage will come, robots will even control humans. It is possible. So, though these are against the fundamental laws of robots, because probably Asimov, though he was a science fiction novelist and used to dream a lot about robots, he may not have thought that robots will become such an intelligent device that will be able to even control or keep humans under control. Now robots are there to track, to trace, to monitor, and even to attack humans. So that is the growth that robotics has seen, especially after the speed of our AI in the science and technology. And coming to industrial robotics, Unimate was the first industrial robot. That was in 1961. So these robots were used to handle equipments or parts like picture tube of TVs for assembly. So that was George DeWall in 1950s, and he has several patents on the first industrial robot. So from a concept in a play to novels, a novel series, and from that to a reality, it took only 20-25 years. So we have a robot at the end. Now, so after almost 50 years, we do have various configurations of robots. With various features inbuilt to each. All these are made to make our life very comfortable in Earth. So fundamentally, robots are here to make humans' life comfortable. Why? Why do we started with from a fiction to a reality? Or what are the benefits we get out of robots? So there are several tasks or processes in an industry. So earlier days, robots became a part of the industry. So demands very high quality work with great amount of consistency. If you see the days where cars were built, automobiles were built, from manual to semi-automated and from semi to fully automated factories, material transfer, material handling, that is a big process. Though it doesn't add any much value to the process, it is a very important process. It demands safety, it demands precision, it demands delivering the materials at the right place, at the right machine, at the right quantity. So, and when factories became 24/7, though we have 3-shift system, we found that robots are much more capable in tasks that are repetitive that requires high concentration, high levels of quality, and slowly for material handling applications, people were replaced with robots, because those days robots were just programmable device. You can use a PLC, or you can have even a hardware controlled logic, or a PLC, or a computer controlled, or an embedded system based. So to realize the material movement, several control systems were possible. So you program the sequence, the robot will operate according to the programmed sequence. Later, we made it to progress to several other fields, especially in the industry, just from material handling to material inspection, material machining. So several stages of several roles have been assigned to robots other than just material transfer. And there are a lot of applications where you need to handle very dangerous materials, especially nuclear field, nuclear material handling. So high levels of radiations. It is not advisable for humans to work in such environment. So another thing is repetitive tasks. No human will like to have a task or a job that is same every day, right? It is boring, though we still have such systems, but we have seen that as experience goes, normally your efficiency should increase, but instead, when you are asked to do a repetitive task, you felt bored, your efficiency may come down. So there are a lot of applications, the human work of such kinds can be replaced with robots. When it comes to quality, especially in building, in assembly, and other applications like gluing, spraying, trimming, deburring, testing, gauging, and other routine laboratory procedures, robots are having higher repeatability and more reliable than humans, so they can do the job better than human beings. Okay, now coming to robots, fundamentally the robots or robotic industry is categorized into two sectors. First is the industrial robots. As from 1950s, you have seen that it is from Unimate to right now around 500 plus robo manufacturers are available throughout the world. So much of I will also show you the statistics of like what is the market, what is the projected market, how many jobs are available in this market. So one sector is the industrial robots. And another sector is service robots. So when you talk about service robots, it includes all other things other than industrial robots. Why we made a grouping like this is so far industrial robots have been the most popular form of robots, but during the last few years, the service sector, especially mobile robotic application, it can be on road, on different terrains, or underwater, or drones like unmanned aerial.
Sir, sorry for the interruption, sir. Prabhakaran from here. Sir, can you share your screen once again?
Oh, sorry, it's not coming.
Yes, sir. Yes, sir. Someone presented, so that's why. You just share your screen once again, sir.
Yeah, I'll do it.
Click. Thank you, sir. Now it's fine, sir.
Okay.
Thank you, sir.
So we have grouped into two groups. One is industrial robots and another is service robots. So whatever that is not a part of industrial robots, it has become a part of service robots. In the service robots, we have UAVs, drones underwater, then the mobile robots for various kinds of terrains. Then there are application based, like robots to take care of elderly people, robots for surgery, robots for helping people, robots like exoskeletons. So there is a big group of service robots. Uh, so initially we thought this market will be very small, but if you look at the market that is developing right now, it has come to a stage that service robots have also reached a stage where it is as big as the industrial robot sector. So this is the industrial robot market. We have also considered the impact of COVID, because all industries, they had seen a sharp decline due to COVID in 2020. But the robotics sector is expected to grow in spite of the epidemic, because one major thing what industries require is social distancing, and if we can eliminate the manual process, the process becomes as safe as, or the most safest will be using automated systems or robots. So it is expected, predicted that by 2024, 75.6 billion US dollars, that is going to be the market for industrial robots. And 2019, we've expected about 48.7 billion. So you can see the growth. So it is an ever increasing market, except 2020, and maybe the effect slightly will be there in 2021, but the market still continues to increase worldwide, especially in India. There is a big boom for robots in industries. We know that most of there is no industry or no automobile industry without robots. Even the cheapest car from India, Nano, that was built by 139 industrial robots. So many robots in manufacturing. If you have seen the video of Tesla factory, Tesla is the biggest electric car manufacturers. They are now into autonomous cars. The factory in San Francisco is about size of 9 football fields and has about nearly 3,000 robots in one shop floor. So that is how the industry is growing. And with COVID, I think more and more robots will be coming to Indian industries also, because wherever if we can avoid using humans, especially working very close, that can be a good solution. And the robots prices are also coming down. There are also indigenous manufacturers. There are 5-6 companies from India who are already into the robotic market. Tata have started making and selling robots in India. Then one MCA robots from Chennai, and PSG has also started our trials are underway. So hopefully by next year, you will see PSG brand of robots also in the market. So there are several other manufacturers coming up from India. So hopefully in another 5 years, Indian robotics market will be totally different. We will be having world-class robots like Fanuc, KBB, KUKA, or Kawasaki. Also, there are universal robots. So a lot of research and development happening in Indian industries too. And to support these industries, there are several institutions. They have started UG and PG programs in robotics and automation. And this shows a comparison of industrial service, these two robotic units. The blue one shows the industrial robots, the numbers in year 2016, 17, 18, 19, and 2020 prediction, estimated and predicted. So 2020, if you see the gap, The gray one is the service robotics field. So in 2016, gray was very small. 2017, it is increased at 124%, whereas industrial robot sector grew by only 32%, though the total segment grew by 50%. In 2018, there was a 5% growth in industrial robots, whereas 61% growth in service robots. 2019, industrial robots, the growth was almost the same, but service robotics field saw another big growth of 33%. And 2020, that is predicted, because still we are in 2020. So both segments, whether industry as well as service sectors, they are going to see a big growth here. Hopefully that will continue. And the prediction is that by 2025, the market will be about 102.5 billion US dollars. So that the graph is shown to make you understand that the gap between industrial and service sectors are reducing. So even by 2020, it is almost level. So probably maybe when we make next year, we have to again categorize under service robotics, what is the share of medical robots, what is the share of mobile robots, underwater robots. So all these put together has come to a sizable number that is in par with industrial robots. You may wonder where we have medical robots in India. Yes, there are 50 plus surgical robots in India. In Coimbatore itself, there are 2 hospitals with surgical robots. So in laparoscopic or some kind of surgeries, robots are used along with surgeons. So robot assisted. It's not that all these robots are totally independent. They can do it on their own, but they are to support the surgeons. So what will happen in the process? Robots are more careful. So whatever it does, it is recorded. It can be reviewed later. Surgical robots can give better clarity to a surgeon. It has vision systems that you can zoom it and see to different sizes. So you will avoid several mistakes that could happen on a surgery table. And it reduces the time taken for surgery. So let us say maybe typically a surgeon does 5 laparoscopic surgeries or 3 to 4 surgeries a day. With a assisted surgery, he could do double of that, or maybe 7 to 8 surgeries per day. And since it is a non-invasive surgical procedure, time required for surgery is less, the strain for the patient will be less, the recovery time also for the patient will be again less, so that he comes back to life much faster than a conventional surgery procedure. So wherever be the field of application of robots, it stands better than conventional methods of the procedure or the process. So if you see the, I'll just skip some of this. I'll go to the, okay. I'll come to some of the general terms. So when you are entering the robotics field, either you want to select a robot, if you want to design a robot, if you want to specify a robot for an application, there are some general terms that are used or popular in this robotics industry. First is the payload. How will you specify, or if you can download the specification or the data sheet of a robot, you can see all these terms defined there. Payload is the ability to carry continuously and satisfactorily a given maximum weight at a given speed. Suppose the specification sheet of a robot specifies it as 10 kilogram. The payload, it says if it is 10 kilogram, that means that the robot end-effector, including the end-effector, if you are using a gripper to grab the component, including the gripper weight, it is 10 kg. It is not that the weight of the job that we are going to lift. It is payload includes the weight of the gripper or the end effector. So if it is a welding robo, it is a welding torch. If it is a painting robo, it is the weight of the paint gun. If it is a deburring robo, it is the weight of the deburring tool. So whatever be the end effector, that weight also should be added. Along with the weight, it should be able to carry continuously, satisfactorily at its rated speed. The velocity means the maximum speed at which the tip of a robo is capable of moving at full extension. It's expressed in like whatever which country it belongs to. You can accordingly the velocity is mentioned. Cycle is the time it takes for the robot to complete one cycle of picking up a given object at a given height, moving it to the given distance, lowering it, releasing it, and returning it to the starting point. So most of the programmed sequence of operations from starting point, complete the entire process, comes back to again the starting point, that we call as the one cycle of operation of a robot. Another important term is accuracy. A robot's ability to position the end effector at a specified point in space upon receiving a control command without previously having attained that position. This is almost very similar to what we describe in CNC machines. So its ability to position, whether the tool or the end effector, that defines the accuracy of the robot. Repeatability means the ability of a robot to return consistently to a previously defined and achieved location. So here in this picture, it can see the difference between accuracy and repeatability. Let us say this red mark, that is the tip of the end effector. In the first case, the target is here, but the end effector, when you program it and try to move, it stops first here, second here, third here, fourth here. So the target position is here, but none of the cycles it is able to reach this point. So here it is having very poor accuracy and very poor repeatability. The second case, though our target is here, the robot is able to position the end effector somewhere close. Every time, if you repeat the same process of cycle after cycle, it is able to reach the same point. So that means repeatability is good, though the accuracy is not good. And in the third case, it is able to achieve the position, targeted position, continuously. Even if you take 100 times, 100 cycles, continuously this is able to, or this particular robot is able to achieve this position. So we say that this particular robot has very high accuracy as well as very good repeatability. Accuracy and repeatability are very important in most of the robotic applications, like machine tinting or welding, because if accuracy, as you know, like of the end effector is poor, we will not be able to perform the operation satisfactorily. And it is not for once, it should be repeated over a number of cycles. And another term which is very popular is a resolution. The smallest incremental change in position that it make or its control system can measure. Again, very similar to a CNC machine, where in a machine, the smallest increment the machine axis can move, or the control system can detect when it moves. So let us say the 0.1 or maybe 1 micron or 10 microns or 100 microns. So what is the smallest increment of change that this able to detect or able to measure or able to move? That is called as the resolution. The size, the physical size of a robot, which influences the capacity and its capabilities, and the size varies according to the what kind of a configuration we are adopting for the industrial robot. Basically, any robotic system consists of these elements. So there is you can just relate to our own human system. So we do have a controller, our brain. If you want to lift your right hand, or when you are using your finger to maybe initiate an ATM money withdrawing process, you know your controller tells your right arm that you have to take the ATM card and insert in the machine. Then the machine asks you some questions. You have to point your finger on the respective buttons. How this process is actuated, how this process happens inside your body. So controller sends the information based on the feedback it receives from the receives through cameras. Then it goes to the brain, and the brain gives actuation signals like muscles and bones to actuate, and accordingly it is moved. The final corrections will be carried out by the controller based on the sensor's feedback. So this is how the basic human system works. Similarly, the basic components of robots. So there is a manipulator, which is very similar to our human hand, and fundamentally this consists of links and joints. It is like a human hand. We also have joints, we also have links. So the robotic system is not much different. It is almost a replication of a human hand. So the teach pendant is used to feed in the program or enter the manual programs or manual commands. The controller receives the commands and gives instructions to the servo motors or stepper motors. Those are the actuators. Or sometimes there are pneumatic robots, pneumatic actuators or hydraulic actuators, and there are feedback systems like encoders or vision systems gives feedback to the controller to correct the feedback loop. Almost the similar things it happens in a CNC machine, but in a CNC machine it is on a controlled axis. If we have 3 axes, the 3 axes are controlled on a plane, which is maybe a cross slide moves on a table, or a table moves on a cross slide, sorry, and we have the job either on the spindle, or there will be tool on the spindle. So very similar thing, but instead of a controlled axis, here it is in a free space. So you will have 3 degrees of freedom. It can be 4 degrees of freedom. It can be 5 or 6 degrees of freedom. Again, degrees of freedom is another term we use it here. Instead of axis in CNC machines, we use here it as number of degrees of freedom. So if a robot specification says that it has 6 degrees of freedom, it means that it has 6 independent controllable axes, possibly driven by 6 servo motors or 6 stepper motors, and 6 joints. So in that case, the number of links will be 7, because every joint will have 2 links, and there will be an end effector at the end. And manipulator is the most important part. It's purely a mechanical unit that provides motion similar to that of a human arm. Various manufacturers, if you see various kinds of manipulators they have designed, considering how fast it should move, considering the stability issues. As you increase the reach of the arm, that means you have to increase the link length. So there may be issues of stability. So according to the application, you need to have an optimized design to have a speed that is possible with the weight on the end effector and should provide stable motion. So it primarily function is to provide specific motions that will enable the tooling at the end of the arm to do the required task. So here we have mentioned each axis is equal to 1 degree of freedom. So typically it comes with 4 to 6 or 7 degrees of freedom. Okay, so I'll come to, okay, end effector is another Normally, if you buy a robot, or if you are planning to buy a robot, industrial robots comes in 6 industrial configurations. You may choose the one which is required for your application. So how is it done depends on several factors that we will discuss. But for the given task, why we are purchasing the robot, we need to have an end effector that should take up the responsibility of achieving the task. So initial days, grippers were the most popular ones because material handling was identified as one of the major responsibilities of robots, why robots were employed in industries. Then later other applications came up. So instead of a gripper itself, there are various kinds of gripping systems: pneumatic grippers, mechanical grippers, electromechanical grippers, 2-finger gripper, 3-finger gripper, grippers with changeable, which can index, and grippers with sensors, tactile sensors, finger-like grippers. So several types of grippers were there. Magnetic grippers. Then came other applications like welding torch, paint guns, power tools, drills, nut drivers, torque spanners. So you name it. Even if, now we use robots for construction. So accordingly, the tool or the end effect can be fixed. So powering up these robots, it can be through 3 of the standard power supplies. So whatever normally what we see in the industry are basically electrically driven, electric power source, and we use servo motors for the axis. Why do we use servo motors, or why servo motors are the most preferred actuators for robots as well as CNC machines? Because it has several unique features which are not there in conventional motors. One is that these servo motors has a high positioning accuracy. It has to achieve this, it has a very special feature called servo lock. So servo lock principle is that once you remove a portion of the voltage supplied to the servo motors, that motor gets into a magnetically locked condition where the power of the stator magnetic field or rotor magnetic field and the power of the electromagnetic field, whether it is on the stator or rotor, depends on whether you are using AC or DC servo motors. But when the power of these two magnetic fields are equal and opposite, it goes to a magnetic locking, and that is called as servo locking. So because of this feature, the motors are able to position it or stop immediately and get locked in that position. So it will stand with the same weight that is carrying without even a slip of, even there are possibilities of even 1 micron. So that way electric actuated robots are highly precise because we use servo motors in that as actuators. Even the application goes for heavy load applications. Like there are also several robots used in mining applications or sometimes in lifting heavy weights. So in those kind of applications and picking and dropping all should be slow, such kind of applications, hydraulic actuators are used or hydromotors are used as actuators in such robots.
Sir, can you please repeat once again?
Pardon?
Sir, can you please repeat once again?
This slide or the last few lines?
Sir, the last 2 lines.
Okay, so I was trying to explain to you like where these 3 power sources are employed. Electric power based robots are used in applications where high precision is required, like applications like industrial applications, especially where whether it is machine tending or lifting or welding, where it has to be very precise. Whereas heavy weight, if there is an application where heavy weight has to be handled, where starting and stopping needs to be very controlled carefully, Then hydraulic motors are employed. Some of the applications of hydraulic actuators comes under mining applications. And pneumatic robots are employed, or pneumatic actuators are employed in robots where speed is important, fast actuation, but may not be as precise as the above two methods of power source. And no, these are not meant for heavyweight applications. These are meant for handling light loads. The system block there in the controller diagram, if you see, most of the industrial applications, the robots are not standalone. So a simple application of a machine tending application where you use a robot for loading and unloading of a component to a CNC machine or any machine. So the robot has to work along with other type of systems. There may be one or two machines. Normally we don't use one robot for one machine because there are plenty of idle time where this robot can be also used for loading another machine. So typical industrial configurations will consist of robots tending more than one machine. So a robot has to work along with other machines, conveyors, inspection tables, material handling systems. So robot controller takes input from various sensors from the field for its own working, as well as to coordinate with other equipments on the shop floor. The controller of the robot runs its own program. Typically, the programming language of robots, some manufacturers have their own standards. Some are graphical. You can just pick, drag, and drop. So basically, a controller receives commands from the user. Then it will be converted into a language that the power devices should be able to understand. If you are using a servo motor in the controller, in the package, the servo motor has to be driven from a servo drive. It needs a power amplifier. So the controller output is given to a power amplifier. Why? Because the robot controller basically is a computer. Computer understands the user program, converts it to binary values that is fed to the microcontroller or the processor in the controller. That again gives output in terms of voltage. It can be analog, it can be digital. Now present day systems are more of digital. That means the robot controller also gives you output in digital values. Means in binary values, which will be equivalent of the command what it has read. That means if the command is that J1 axis to rotate at 180 degrees at a speed of 2 meters per minute, then while it reads the program, it will convert that command and will drive. There will be a servo drive for the servo motor of J1. So for the servo drive, it should keep on supplying voltage or values of binary values that the servo drive will understand. Okay, this is a command that I should be able to drive the power up the servo motor to rotate 180 degrees. So to make the 180 degrees rotation possible, how much of pulses it has to send to the drive, and accordingly how much of voltage. Finally, the motor will understand only analog voltage. Motor will not be able to understand binary values from the controller. So let us say it is a 200 volt AC servo motor, 200 voltage to the three phases at the programmed sequence, and how much of time it should require to achieve 180 degrees. That will be based on the speed as well as the feedback from the encoders or from the pulse resolvers. So the controller or the drive will calculate how long this voltage should be applied across the motor terminals, and that will be applied so that the motor rotates to the 180 degrees and stops. The stops as soon as the power is withdrawn from, or it goes to the servo locking situation. So fundamentally, the most of the robotic systems will have these elements. Okay, I'll skip this. This is about mobile robots. Okay, I'll come to the industrial robots because our topic is about that. Here you can see pictures of 5 different types of industrial configurations. The last one, the parallel, is not shown here. Hopefully, I think it will be there in the next slide. So, first is the Cartesian or the gantry robo. Second is the cylindrical robo. Third is the spherical. 4 is the SCARA. 5 is the articulated. And 6 is the parallel kinematic. So how these configurations are achieved are based on how the links and joints are connected. So just give me a minute. So the anatomy consists of the links and joints. So we'll see what is the meaning of this. Fundamentally 2 types. One, the motion can be translational. So this will happen in 2 cases: when the joint is linear as well as orthogonal. So these are the first 2 types. So there is an input there. Let us say there are the links, we consider it as one is input link and another is output link. So there is a joint motion possible, like a telescopic antenna, right? So one link can move inside the joint. That is called as a linear joint, and it is represented as L. And there is orthogonal joint, and here the output link is orthogonal to the input link. It is like a normally T junctions of pipe fittings. So that is represented by O. Then there are rotary motion, rotational joint type R. Then we have twisting joint T. And there is another one, revolving joint V. All these 3 things you can in fact experience with your hands. So you can just rotate your joints in your hand, maybe in your wrist. You can twist. You can also revolve, like your shoulder, you can revolve. So these are the 5 joint motions available in any manipulator that is used in industrial robots. So whatever be the configuration we are going to discuss, all these things are based on these 5 configurations of the joints. So the notations, example TLR means that it has a twisted joint, a linear joint, and a rotational joint. So if a robot with TLR means it will have one twisting joint, a linear joint, and rotational joint. And then you will be able to find out what is the architecture of this robot. Probably you can try this. TRT, R, TVR, TR, RR, T. So twisting, rotational, twist, rotational. So how the configuration will look like, you can just sketch it and see. Maybe you can see as an assignment, right? And now it is shown here. One twisting joint here, one rotational here, another twist here, another rotation. So if the robo configuration is like this, then possible motions are this. Second is twist here. You can see the joint 2 is revolving type, joint 3 is rotational type, joint 4 is twisting type, and joint 5 is again rotational type. So this is another configuration of an industrial robo. Here you can see that RRT. So first is fixed one. There is no joint. Here. Here joint number 1 is rotational. Joint number 2 is again rotational, and joint number 3, or maybe the end effector, is connected to a twisting joint. Normally, end effectors are connected to twisting joints. So this is RRT. So this is a typical articulated robo configuration. So if you just understand this, we'll be able to find out what configurations are. So any joint notion will consist of symbols L, O, R, T, V to designate joint types used to construct the robot manipulator. Separates body and arm assembly from wrist assembly using a column. So if there is a column mentioned here, that means it is used to separate body and arm assembly from the wrist assembly. Because wrist assembly is where the tool or the end effector is fixed. Is it clear? This is a fundamental of how you represent the architecture of any robo. Okay, performance specifications, we have seen this, general terms, work volume. Okay, these things have been done. So the SCARA, the notion is VRO, rotational, revolving, rotational, and orthogonal. The expansion of SCARA is selectively compliant assembly robot arm. Where do we use? This is one practical case application of a SCARA. SCARA robots are more popular in applications where high repeatability is required. Typically, the number of axes are less, 3 to 4 axes normally. And since being less number of axes, it takes lesser time for motion. So wherever you want speed, like pick from a conveyor, place it somewhere, pick from a another inspection station, transfer it to another thing, or maybe just put and pick up in bins, sorting, such kind of applications. SCARA robots are very popular and they are very fast. Cylindrical robo arm, notion is TLO, so a twist, then a linear, and there is an orthogonal movement. So these robots consist of a vertical column relative to which an arm assembly is moved up and down. This varies according to the size of the length of the arm. The size varies and its range varies. These are very simple robots, maybe the cheapest of the versions in the robots. These are not meant for picking up big objects and keeping it. But small robots are used for precise material handling application. Then next is the jointed arm or the articulated. It consists of TRR. Basically, this is the base, and which moves on the another one, fixed one. So that axis is or that joint is the twist. Then rotational axis can be 3 or 4 or 5, so it depends. And the last one also sometimes will be a twisting joint. So these are jointed arm. These are employed in various applications in the industry. up to a payload of 130 kg or 150 kg are available. They are fast, but not as fast as the SCARA or parallel kinematic. Typically, they are find applications in welding, painting, sealing, deburring, and also for pick and place or machine tending applications. Polar coordinate is not that popular these days because of the features or facilities available in other robots. But still, there's a configuration called Polar robot. This were the, if you see the Unimate robot, this was almost the same configuration of Polar robot. Repeatability is not that good. Normally 3 or 4 axes. But the advantage is it has a big or large vertical envelope. So if you want to pick something from ground and lift or reach to a height, then this configuration is the best suited one. And it is not meant for high-speed applications. Sometimes we use it for spot welding or loading ASRS stations. Cartesian robo, the configuration is one linear and 2 orthogonal, consists of 3 sliding joints, 2 of which are orthogonal. And it is very similar to the XYZ of a vertical CNC machine kind of an arrangement. These robots find a lot of applications, especially in inspection, then assembly, gluing. Typically, they give a better repeatability. Since there are only 3 axes, it moves on. The work volume is also limited, but it can be based on the length of X, Y, and Z. The envelope can be over a large space. And typically not meant for huge heavy weight carrying, but up to 100 kg this carries. And since being like a 3-axis machine, it is fast enough to move materials. Sorry. So some of the industrial applications you can see it is like a conveyor or a overhead crane. It can also be used. And this is the last one, the parallel or parallel kinematic, or sometimes called as delta robots. This is all other robots. If you see, they are serial robots. Each manipulator or each link is connected serially, but here it is parallelly connected. That is why it is called as a parallel robo. You can see a typical work volume of a parallel robo from ABB. So such kind of, if your reach is within this work volume, these robots are the best suited. The one core benefit is they are very, very fast. So pick and place applications, it finds a lot of applications, especially in electronic PCB assembly, food packing, like connectors. If you have a 40-pin connector, the 40 pins have to be fixed at the right place or right slots, and that can be done very fast using these robots. So these are the 6 industrial configurations of robots. So I think we have come to a time where I should let you to ask some questions. So that is about the history, where the industry robots stands now, how big is the industrial robot market, how big is the service robotics market, what are the, how you normally represent an industrial robot in terms of the most popular 6 configurations. So now I think you'll be able to understand when, if you look at an industrial robot, what kind of a configuration this belongs to, how many degrees of freedom. You can understand the common terms like work volume, payload, accuracy, resolution, all these things you'll be able to understand and appreciate. And let us also understand the applications. So a lot of videos, I don't want to play videos here because video in an online course may not synchronize with the speed of the presenter sometimes. So we avoid showing videos, but please go through several videos, application videos available in YouTube or in various websites. Some of the major manufacturers of robots are Fanuc, ABB, KUKA, Universal Robots, Kawasaki, Puma, Yamaha, a lot of robots. You just name it, hundreds of robots are there. And please watch some of the applications of where these robots are employed. Any questions? I also promised you about the COE welding. Let me see whether it is available. Very quickly, I will just show you the Center of Excellence in Welding Engineering and Technology, what we have established here. So we have several robots here, around 12 industrial robots are there. What we have done, one project is that using a universal robo, we made, this is a ROS-based robo, so that robotic operating system can be used to control this robo. So calibration is done. We made an app-based control of this robo. Some of the typical specification of UR5. It's a small robo with a payload of 5 kilogram, a reach of 850 mm, with a total weight of 18.4 kilograms, so that you can even lift it and take it to a classroom. It works on a single phase supply with a very good repeatability. So we try to, these robots are not meant for welding, but we try to integrate a welding power source with this robot and demonstrated how welding can be achieved. These are some of the other robots we have in the welding center. We also have a Kinova. Again, this is a ROS-based. Okay, the UR5 and this Kinova, they are called as cobots, not industrial robots. Cobots means collaborative robots. Collaborative robots is the new term or new kind of robots in the industry, because this can work along with human beings. Earlier days, industrial robots were typically inside a cage in the industry, because humans are not supposed to enter the cage during the robo functions, because humans can get hurt. But cobots are made with sensors that if it hits somebody or it is going to hit somebody, it will stop. It will see that humans working closer to robots are not harmed. So that is another new term in industrial robots, cobot. So this, unfortunately, the course has become online. If it would have been happening inside the campus, we all would have got the opportunity to program, play, and move these robots. You could have done some experiments here, but all these facilities are available with funding from Ministry of Department of Heavy Industries as well as from PSG management. Altogether, the investment is around 30 crore. That is various types of power sources. We have welding power sources available here. So I think we have 2-3 minutes for some questions if you have any.
Participants, if you have any queries, you can unmute and you can ask your doubts, or else you can type in the chat box so that the speaker can answer for your question. So there is a question in the chat box.
Differentiate the number of axes.
Differentiate the number of
axes and degree of
freedom in the robot.
Yeah. Okay. So I understand that you know about the program. Pardon?
So may I know that what is the stand of India
on
robotics and its development?
So I think if you can just type it now in the chat box, I think it will be easy for me to read. So meanwhile, there is one question.
Sir.
You just type it. In the meanwhile, I'll answer the first question. It says that differentiate between axis and number of degrees of freedom. Okay. So I understand you will be able to, you know that about the number of axes in a machine. So maybe one axis. A lathe will typically have 2 axes. If it's a VMC, 3 axes or 3+. So one axis means one direction of movement in maybe X direction, Y direction, or Z direction. To make this movement happen, there is a motor a rotary motor, and that rotary movement is converted to linear with the help of a ball screw and drive. So the table moves over the ball screw, and the rotary motion is converted to linear motion. That is one axis. Recent machines, instead of rotary to linear conversion, there are linear motors also. So that is one axis. Since it is a controlled movement, the start point, end point all have limitations, and it is only on one particular direction, whether X, Y, or Z. We call it as the axis. But in case of a robot, it is not one axis. One joint can move in X direction, Y direction, Z direction, or any direction. So typically an end-effector's movement is based on the movement of more than one joint. We can also move by one joint, but it consists of a simultaneous movement of 2 or 3 axes, means 2 or 3 degrees of freedom. So a degree of freedom here means that it is one axis, but it is not limited to one direction. It can be on a free, it is on a free space. It is on a 3-dimensional space. That is why it is degree of freedom. India stand on robotics development. Yeah, India has been a consumer of robots so far, industrial robots. I think 2019, totally 3,568. That was the number I got from some of the user websites. So around 3,500 robots were sold last year. This year, it is expected that around 5,000 robots will be sold in India. With that, India stands around the 12th worldwide in terms of consumption of robots. But it is expected that within next 5 years, India will become the 5th consumer of robotics. World's #1 consumer of robotics is China. When we consumed or installed 3,500 robots in 2019, China installed around 104,000 robots. To see the difference. Though China is also more populated than India, or more, is another populated country, their number of installations per year doesn't have any reflection on the number of people, because it is just by introducing robots, there is a myth that it will take away humans' job. It's not like that. That is already proved by China. So we also are moving right now at faster speed of robotization. Is your college affiliated to Yentra Lab? Yes. Will you focus the hands-on practicals on any software? The Yentra Lab in our center consists of not just Yentra, the next-gen kits. So we do the programming on the kit or on the system and then transfer it to the kit. You can do it in C, or students can use free to use any of their programming languages. But basically, it is just trying programming, transfer it to the robots and see how the robot, it may be a line follower robot, or it may be from point to point robot. Along with that, we have other robots here. We have Tektronix, we have, Lego kits. We also have Vex robots. So fundamental robotic lab in the first year allows the students to work on all these robots. Sorry, I missed question. Sir, how to choose power source, AC or DC? For the servo motor or for the... Okay, so I think I understand this may be for a servo motor. So fundamentally, both categories are available. If price is important, price is of your major concern, then better to go for DC servo motors that are cheaper. But if performance and less maintenance, if that is a concern, then better to go for AC servo motors. Okay, I think time up, so I'll stop with this. Still, you have any questions? We are here for the next 5 days, so I think organizers will share my mail ID, or I can share it, so that if you have any questions, you can write to me. I can share my mail ID here.
Thank you, sir.
Thank you, sir. The session is very interesting and informative, sir. We also got more inputs and knowledge on various industrial robots and its architecture. Thank you, sir. I request all the participants to join back at 3:45 session.
Yes, sir.
Thank
The
you.
session will start